Welcome to Pomodoro Joe for Saturday, September 16th, 2023. Today we're doing LeetCode problem 1631, path with minimum effort. This is a medium problem. You are a hiker preparing for an upcoming hike. You are given heights, a 2D array of size row by columns, where heights at row columns represents the height of the cell at row column. You are situated at the top left cell, 0, 0, and you hope to travel to the bottom right cell, rows -1, column -1, i.e. 0 indexed. You can move up, down, left, or right, and you wish to find a route that requires the minimum effort. Okay, but what is the minimum effort? Well, a route's effort is the maximum absolute difference in heights between two consecutive cells in the route. Okay, I'll say that one more time. The route's effort is the maximum absolute difference in heights between two consecutive cells in the route. So for any two cells, the effort is the absolute value of the difference. So to go from 1 to 3, that will be a 2, and to go from 3 to 5, that will also be a 2. But a route's effort will be the maximum effort of any of these efforts. So now our goal is to return the minimum effort required to travel from the top left cell to the bottom right cell. So here's our example. We have 1, 2, 2, 3, 8, 2, 5, 3, 5. Those are our rows. Now, to go from 1 to 2, that would require a minimum effort, or a smaller effort than to go from 1 to 3. But if we went from 1 to 2, let's see, 1 to 2, 2, 2, so these would all require low efforts. But to go from 2 to 5, so these all require 1 or 0. So 1 to 2 requires 1, 2 to 2, 2 to 2, those all require 0. So far, if we went this route, we would have maximum effort of 1. But to go from 2 to 5 is going to take 3. That's a maximum effort for this route, is 3. But it turns out that the best route is to go from 1 to 3. So that actually requires more effort initially, but that is an effort of 2. 1 to 3 is 2, 3 to 5 is 2, 2, and 2. So our total maximum effort for this would be 2, whereas the other route would be 3. So it turns out that this is actually our better route. Okay, and we have a couple other examples, some fun ones. All right, so we'll put 25 minutes on the Pomodoro timer and we'll get started. If you've been watching my videos, we've seen things like this before, so we can definitely do this, and we definitely don't want C++. Let's get to Python here. All right, so let's start with some result. We'll set it equal to infinite because we're looking for a minimum effort. So let's start with something big and then we'll return our result at the end. All right, so we'll traverse this graph by looking up, down, left, and right from every cell. We'll just do our standard graph traversal. We'll start at the top left, 0, 0. Then we'll just move up, down, left, or right, depending on which cells we can actually get to. And we'll record what the minimum effort was to get to that cell, or maybe the maximum of the minimum efforts it took to get to that cell, or the minimum of the maximum efforts it took to get to that cell. That's really the way it is. All right, so let's do this. Let's start with some Q, where we're gonna start at 0, 0. So I'm just gonna have tuples, 0, 0. And then while we still have some element in our queue, we'll just pop some element off the queue and we'll calculate its effort. So let's see, while we have a queue, let's get a cell, so that's going to be q.pop. I'm going to pop at index 0 to make this a breadth first search. And now from this cell, we have to look up, down, left, and right and calculate the effort it's going to take to get to the next cell. Let's do up, down, left, and right. So up will be x, and then y minus 1. So because these are rows and columns, this is sort of a screen space type coordinate system, where 0, 0 is in the upper left, and we increase our x as we go to the right, and we increase our y as we go down. So that means we decrease our y to go up. So up is going to be x at y minus 1. That's only if y is greater than 0. Otherwise, we can't go up. There is no cell above us, and in that case, we'll have no up, so else none. All right, and then down, very similar. We're going to have x and then y plus 1, but that's only if y is less than the maximum y, else none. All right, I don't have this max y, so let's actually calculate our max y out here. So our maximum x, well, this is the number of columns we have, so that's going to be the length of our heights at index 0, that's one row. And our max y, that's going to be the length of our heights, that's how many rows we have. All right, so I have my up and my down, now I need my left and my right. All right, now one thing I noticed while I was doing this max x and max y, I actually calculated the number of elements here, not the max index, so I actually need to subtract 1 to get the max index for max x and max y. All right, now I'm going to throw all of these directions into a list here. So I'll have directions. That's just going to be up, down, left, and right. And that's going to let me iterate through all these directions. All right, now we're going to go through every direction. Let's look up, down, left, and right and calculate the effort it's going to take to get to that cell. So for every direction in my directions, first let's check to see if we have a direction, because it could be none. So if D is equal to none, we'll just continue. Next, let's calculate the effort. So the current effort to get to that cell. That's going to be our height at this cell, which we haven't calculated yet, or we haven't looked up, so we'll have to look that up. That's the height at this cell minus the height at that cell, and we take the absolute value. So it's going to be height. Let's see, I'll have some, it's going to be y first. Our direction's y, so y comes first, and then x. All right, let me get my dx and dy out of here. So this is a little weird. The x and y are going to be stored in standard Cartesian coordinates, so x first and then y. But when we look them up, the row comes first in our grid and then the column. So it's going to be y first and then x. All right, now this height, I haven't actually pulled that out, so let's grab this height. So what's the height for this cell? That's going to be the heights at this yx, and I haven't pulled that out either. So let's see. Our current x and y is this current cell. All right, so I have my current cell, I have my current height, I'm calculating this new height, and this is actually going to be the absolute value of this delta, so ABS. And now I need to check, is this new effort the maximum effort on my route so far? Otherwise, I'm going to have to keep track of my current maximum effort so far. Now, I don't have anything to do that just yet. So there are a couple ways to do this. We could have a dictionary where we have our key value pairs, where the key is our cell, and the value is our current effort to get to that cell. Or we could have another matrix or another grid that's the same dimensions as our current one, just filled with the effort it took to get to that cell. So let's do that. So I'll have an efforts list or matrix. So the first one, I'm going to fill it with infinite because we don't know the minimum effort it took to get to that cell. So we'll just say it's going to take the maximum effort to get to the cell until we find a better value. So that's going to be infinite times, let's see, I need the max x, but I need max x plus one of them. So that gives me one row, and I need max y rows of these. So for in range, max y plus 1. Okay, so this will create a grid that's filled with infinite, and it's going to be the same dimensions as our input heights. So we'll just have, basically you can imagine this same grid here, but it's just filled with infinite. Now when we find a better option, a better effort, then we can replace that infinite with our better effort to get to that cell. So right here, we've just calculated the current effort to get from our current cell to this next directional cell. And now we can check, is this effort our better option than what's already in that cell? So if this current effort is less than whatever we already have in this cell, so we'll look at our efforts for this cell. Let's see, it's going to be our dy and dx. So now we just found a better way to get to this cell. So let's replace this. So our efforts for dx dy or dy dx equal this new current effort. And we'll take this cell and we'll put it in our queue, because now that we've changed the effort that it took to get to this cell, we need to reevaluate all the cells that come after this cell, because we might get a better answer. So let's put this cell into our queue. All right, so now we've put the direction in the queue, and we'll keep popping cells out of our queue, keep moving down until we find the maximum effort to get to our final cell. Okay, so we're almost there, but there's one piece that I'm missing. So this will take me to the next cell. What's the current effort to get from this cell, the cell that we just popped out of our queue, to the next directional cell, up, down, left, or right? That tells me the current effort it's going to take to get there. But it might have taken me more effort to get to my current cell than it's going to take to get to my next cell. And we're looking for the maximum effort for the entire route. So that means I have to look at the effort for getting to this cell and check to see if that's greater than this current effort. If it is, then that's actually the effort it's going to take to get to the next cell. So let's grab my effort here. So effort is the effort it took me to get to this cell that we're evaluating. And we have to check that against the effort it's going to take to get to the next cell. So maybe I should call this next effort. That might make it better. Okay, so in this case, the next effort will actually be the maximum of this next effort or our current effort. All right, this is kind of confusing, so I'll go through this one more time. So we're at some cell. Let's say we're at this 3 cell here. So we're at some cell. We need to look up, down, left, and right at our next directions that we can get to. Then we'll calculate the effort it's going to take to get to that direction. That's the next effort. Now that's going to be the effort that it takes to get to that cell, but we're looking for the maximum effort for the route. So we need to check to see if the effort it took to get to this cell that we're currently evaluating is greater than the effort that it takes to get to the next cell. If it is, then in that case, the effort it takes to get to that next cell is just the maximum effort it's taken so far on this route. All right. And let's see, looks like we're not using this result at all. We can get rid of this result. And instead of returning result, we can return. Now we're keeping track of our efforts. We can just return our efforts at max y, max x. All right, let's take a quick look. So we're going to create another grid that's just filled with infinites that's the same dimensions as our current heights grid. Then we're going to put 0, 0 onto our queue. Oh, and one thing I didn't do, I need to set my initial value for this. So the heights for 0, 0, or the efforts for 0, 0. So the effort to get to 0, 0 is just 0. We need an initial value for this one. Now, while we still have some cells in our queue, we'll grab a cell out of the queue. We have our directions up, down, left, and right. We'll just look at every direction up, down, left, and right. If we can go in that direction, we'll check to see what's the effort it takes to get to that next cell. Now, if the effort it takes to get to that next cell is less than the effort it took to get to our current cell, well, then that gets sort of overshadowed by the effort it took to get to our current cell. Now that we have our maximum effort, our next effort, if that next effort happens to be less than what we currently have as our best effort to get to this next cell, well, then we can replace that. We have a new, better way to get to this cell. So we'll replace that effort with our new next effort, and then we'll have to put that cell back onto our queue, because now that we've changed the value there, it might affect the surrounding cells. So we put that back into the queue and we'll evaluate it again. And then at the very end, we should have our answer at the very last cell here. Okay, let's run this and see how we do. Oh, I didn't pull out my X and Y up here. I need to do this before I start using them. All right, let's grab that up here. Okay, seems to work. Let's see if we can pass all the tests. And we pass. Let's see, we don't do great. We only beat 24% for runtime, 81% for memory. That's not great. One quick thing we can do here, instead of using our standard queue, we can use a deck. That should give us a little bit more speed when we pop values out. So we'll have to do a pop left. Let's see how this goes. Doesn't really help us at all. That surprises me. All right, I think we do a little bit better in memory. Maybe we just do a little bit better in memory. Weird. All right, something else we can do. We got this absolute value and this max. Let's change this max to say Next effort will equal next effort if next effort is greater than our effort, otherwise effort. All right, this is our own sort of max calculation. All right, let's try that. Gives us a little boost, not a lot, 27%. 98% from memory though, that's fantastic. All right, well, I think that's it for me. I hope you enjoyed this. I hope you had fun. I hope you learned something. I hope you can go out and write better code.